Hello and welcome to seminar number 20. Today we are going to talk about gamma spectrum. For those of you who don't know, these presentations are held on a Discord server called the Red Zone. Most of the time it's on Sunday evening, German time. If you're interested, feel free to join and let's get started with today's presentation. So, the plan for today is why bother with gammas and what does a gamma spectrometer look like. And then we are going to compare the semiconductor versus the scintillation counter and its efficiency, energy-dependent efficiency, and its energy resolution. And then on the last slides, we are going to look at a typical gamma spectrum. So why bother with gamma spectrometry? First of all, it's a non-destructive type of analysis, meaning that you don't have to destroy your sample in order to analyze it. For example, if you do mass spectrometry, you have to dissolve your sample. If you do something else like LSC, you also have to dissolve your sample, but first we do the non-destructive analysis, for example gamma spectrometry. You can just put your sample on the detector in its closed vessel and there you go. As I said already, you just have to put on your probe onto the gamma spectrometer, so you don't have to do any preparation. There is little inaccuracy because the gamma lines are very well defined. Depending on the gamma spectrometer that you're using, you might have, when you're using a semiconductor, like an inaccuracy of plus or minus half a kiloelectron volt, which is quite accurate to be honest. And most of the radionuclides have gamma lines. There are very few examples of them not having any gamma lines. Some of them you might have to measure for long, but there are some examples like phosphorus 32 or sulfur 35 which do not have gamma lines at all, but most of the time you know that you're working with these radionuclides, and most of them are short-lived, meaning that you most likely purchased it yourself and you don't have to analyze it as much. Okay, what does a gamma spectrometer look like? For example, here we have our one gamma spectrometer. On the bottom left, you have a dewar with liquid nitrogen because the semiconductors all have to be cooled with liquid nitrogen. The high purity germanium detectors only have to be cooled during measurement time, but the older version, the lithium-doped germanium crystals, have to be cooled all the time, and this one is a GeLi. This is what we call a lithium-drifted germanium detector. These are of the older type, and there we have the dewar for the liquid nitrogen to cool this down, and the cooling happens via a cooling finger, which you can see here. This connects then to the detector crystal, which is also shown here, and this receives all of the gamma energies. You can see all of this sticking up here, and then it goes down into the liquid nitrogen dewar where it's cooled. And then we have the lead castle to reduce gamma background noise. So we can only measure our sample, which would be placed here. Okay, let's address a very typical exam question. Please compare the semiconductors versus scintillation crystals. So, if you take a semiconductor in general, like silicon or germanium or arsenic, for example, they have a band gap between the valence band and the conduction band. The band gap is very small, but it's there, meaning that they do not conduct electricity just on their own. So you have to apply some energy to the electrons to promote them from the valence band into the conduction band. This band gap is, for example, with high purity germanium, just 0.66 electron volts. So if you apply 1.66 electron volts to one electron, it will be promoted into the conduction band. But in nuclear chemistry, we are measuring ionizing radiation, gamma radiation, which is in the kiloelectron volt to mega electron volt range, which greatly surpasses the just 0.66 electron volt. Meaning that if one gamma radiation photon will hit a crystal, it will not only produce just one electron hole pair, sometimes called excitons, but it will produce many of these excitons. And the amount of excitons created is greatly correlated to the energy deposited in the detector. The more energy is deposited in the germanium detection crystal, the higher the amount of excitons is. So if we have a high energy photon and it deposits all of its energy into the germanium crystal, you will see a difference in the amount of excitons created as opposed to a lower energy gamma photon, which will not produce as many excitons. This was a very short overview on how semiconductors work. But if we now compare them to scintillation crystal, for example, thallium-doped sodium iodide, you can see that we have the same sample, cobalt-60, measured with the lithium-drifted germanium crystal, so a semiconductor, and with a scintillation crystal. And you can see a huge difference in the spectrum. This is because sodium iodide is an electric isolator. So the aforementioned band gap is much higher, meaning that, if you want to say it like that, there is more energy lost before the creation of excitons can occur. So you will have fewer electron-hole pairs if the same energy gamma rays hit the sodium iodide thallium-doped crystal, meaning that you will have a lower resolution. For example, if you take a high-purity germanium detector, a hypothetical gamma photon will create 1000 pairs of 1000 excitons, and the error of the measurement is equal to the root of the count rate. In this case, it's just the root of 1000, which is 31.6, meaning that the proportional error is 31.6 divided by 1000, it's 0.03% uncertainty. But the same energy gamma photon will create in a sodium iodide crystal only 100 pairs due to the higher band gap, meaning that we have the same error, which is just the root of the count rate. So the root of 100 is 10 and the proportional error is 10% as opposed to 0.03%, meaning that you have a higher uncertainty, and this is why these bands are so broadened as opposed to the germanium drifted or high purity germanium crystals. It's a very typical exam question, okay? So let's take a closer look at a typical gamma spectrum, which might look something like this. This is not background corrected or anything, and we can see a few peaks. The first peak is at 1368 kiloelectron volt, and another one is the 2054 kiloelectron volt peak. These are the so-called photo peaks or full energy peaks, and with these you could determine the radionuclide that I was measuring. If you want to, go ahead, look up in the isotope browser app, type in those gamma lines, and you might be able to figure out which radionuclide I used. And I used sodium-24, which has these two gamma lines. In addition to these photo peaks, which are directly correlated to sodium-24, we can see additional peaks, for example, the 1461 kiloelectron volt line, which comes from potassium-40. Now, I didn't have potassium-40 in my sample, but we can still see a peak in there. I will get to that later. In addition to that, these peaks are very high in energy, and if a photo peak has an energy of above 1022 kiloelectron volt, we can see some additional features in the gamma spectrum. For example, the first and second escape peak. The first escape peak is at the energy of the full energy peak minus 511 kiloelectron volts. And the second escape peak is at this energy minus 1022 kiloelectron volts. Now, the 1300 is also above 1022, but the occurrence probability for these escape peaks increases with energy. So you might be able to find these if you look closer, but here we can see them quite clearly because this is a very high energy. In addition to these peaks, we can also see a very big peak here, which is at 511 kiloelectron volts. If you look at the chart of nuclides, you can still see, there we go, we have these two photo peaks, and we have all of this other stuff, which I will get to on the next slide. So, why 1461 kiloelectron volt? It's coming from potassium-40, which is everywhere, and it's primordial, as we can see here from the half-life. Potassium as an element is just everywhere, and everywhere where there's potassium-39 and 41, there will also be the potassium-40, which is radioactive and emits this very high energy gamma line, meaning that this very high energy gamma line will also get through our lead castle that we've built around our detector. You will have this peak in every gamma spectrum if you don't background correct it. So if you're just measuring just background noise, you will get this peak. In our case, in the lab, it's mostly in the form of just concrete, and since pretty much every wall is made from some type of concrete and includes potassium-40 or just normal potassium, and alongside that we'll have the potassium-40, you will see this peak. Interestingly enough, this peak does not come from the most amount of decays. Potassium-40 has two routes, the beta-minus decay and the electron capture beta-plus route. And during the beta-minus decay, which it does most of the time, it will form the calcium-40 nucleus, a double magic nucleus. However, this decay is not associated with any gamma lines. What is associated is the decay into the argon-40 nucleus, which is in an excited state and will do an isomeric transition, emitting this 1461 kiloelectron volt peak. This decay only occurs 11% of all the time, and the rest goes into calcium-40. Now, calcium-40 is the double magic nucleus, which means that its excitation energy is very high, which cannot be populated through a just normal beta decay, meaning that this decay occurs without a gamma line, and our very prominent gamma line from the potassium-40 will only occur at most 11% of all the decays from potassium-40. We also have seen the 511 kiloelectron volt peak, and there are two factors attributed to this. One factor is pair production. 1461 is higher than 1022 kiloelectron volt peaks, and this can lead to pair production. So the production of a positron-electron pair, which occurs in an atomic nuclide field. So if this photon comes near a field of an atomic nucleus and is high enough in energy, it will produce an electron and a positron according to E equals mc squared and some leftover energy depending on the difference. And this positron can annihilate with other electrons in the surrounding area, and then there will be an emission of two 511 kiloelectron volt peaks, which the gamma detector could also measure. Now, this is why the 511 kiloelectron volt peak is a bit more pronounced in scintillation crystal using sodium iodide, because iodine just has a higher atomic number, and the rate of pair production, or the occurrence probability of pair production, is correlated to the atomic number. And iodide has a very high atomic number, whereas germanium has a much lower atomic number, meaning that you will have a more pronounced 511 kiloelectron volt peak in scintillation crystals using sodium iodide crystals. And of course, some thallium is in there also with a very high atomic number. More facts about the gamma spectrum. If you just look at one peak, for example, cobalt-60 or cesium-137, you could see before every peak a correlating Compton edge. This marks the area where there is the most amount of energy deposited in the crystal without a photo effect. So a gamma photon hitting an electron and being Compton scattered and not doing a photo effect, because via the photo effect you will get these photo peaks. But if it's scattered, it will have some energy left, and this difference is the amount of energy left for the photon that could still exit the crystal without transferring more and more energy until it eventually deposited 100% of its energy in the crystal, leading to yet another photo peak. Then you have the backscattering peak, which is basically the same. So you will have this backscattered photon with this difference in energy, which could also happen not inside of the detector, but outside the detector. And only this backscattered photon will get into the detector and can be measured, therefore leading to a backscattering peak. And then in addition to that, if you're dealing with very high activities, which will also lead to very high dead times, there could be yet another peak, which is called the sum peak, where, for example, if you have a very high cobalt-60 activity, you will have an additional peak, which is 1130 plus 1170, which is 2500 kiloelectron volts, meaning that these photons come in at such a fast rate that the detector just sometimes can't distinguish between two of these photons coming in at different times, and will just sum them up and form a peak at a much higher energy correlating to these photo energies. Here if you want to take a closer look. With that being said, thank you for your attention and goodbye.